Hi. This is my talk about sparse virtual textures. It's uh, substantially similar to the talk that I gave at GDC 2008. I apologize for being a disembodied voice, but I couldn't find a way to point the camera at my slides and at me and let me see the slides as well. So I want to start off by showing you sparse virtual textures in action. And in fact, I already did start that off because this is not actually PowerPoint. What we're looking at right now, we're actually looking at my sparse virtual texture demo. So what we're looking at is a 16K by 12K texture, virtual texture, that I've painted onto a single quad here. And then I have a landscape in the background that's a 64K by 64K texture, as well as some planets with some data from NASA, which add up to, I think, another 8K by 8K. You can see there's detail all the way down. It's not a very good procedurally generated frame there. The slides are procedurally generated. I have text files describing the slides and turn those into bitmaps and then generate the texture data on the fly as you need it. So if I go in here, you can see the slides to some level of detail. And if I go in too far, you can see that they're still made out of pixels. All right, so that's that. Let's go ahead and get started. This is the virtual texture that I'm going to use in illustrations. So typically this would actually be a very large texture, not as small as this one is, and it would probably look nicer. So what we want to do is we're going to render as if we had this virtual texture in memory, but we can't fit this virtual texture in memory, so we have to fake it. So the first thing we want to do is figure out which texels we actually do need to have in memory, because they're texels that we need to use to draw the scene, rather than all the unused texels that are occluded or too far away or behind the camera. So somehow we're going to figure this out, and I'll talk about that later. Once we figure that out, though, that's too much. The data there is too detailed to work with, so we're going to divide the virtual texture up into fixed-sized blocks that I'm going to call pages. For each page, we're going to look if there are any active texels in it. If there are, we're going to make the entire page active. And at this point, this is the quantization we're going to use. This is the data we need to actually hand to the graphics hardware so we can actually render the scene. So let me make a little room here. On the left is going to be the virtual texture, and on the right is going to be the actual stuff we put into the hardware. So I'm just going to download all of those texture pages, and I'm going to, there's a little bit of junk here at the bottom, but there's all the texture pages we actually need. I'm going to pack them into one texture. Now they're just totally arbitrarily packed in there. It doesn't matter what order they're in. I happen to do it left to right, top to bottom. But you see that there are these transitions, and typically there's at every page boundary, there's this totally arbitrary transition to some other page in that physical texture, the actual texture that's in the hardware. Okay, now if we want to actually sample from this virtual texture, right? I'm going to, I'm starting to use the word. I'm going to put in my geometry these virtual texture coordinates and just address this virtual texture. My geometry just isn't going to care at all about the virtual texture's existence. It's just going to think there's this big giant texture. So if I want to sample from some point in that virtual texture, in my pixel shader, I need to somehow translate my attempt to sample from that coordinate in the virtual space into the actual physical coordinate that actually matches, that has the data that I'm looking for. So to do that, because I have these pages, I can actually just figure out which page corresponds to which page. So to do that, I'm going to make something that's called a page table, since that's what virtual memory systems call it. And this page table is going to tell me how to map from the virtual pages to the physical pages. So it's going to be the same size as the virtual texture coordinate, in the sense that for every page in the virtual textures, I have one page table entry in the page table, which means I have one texel in this page table texture. So there's one texel per page. And what data I put in? Well, somehow I want to make it so that when I sample from the texel that corresponds to the page I'm looking at, the virtual page I'm looking at, somehow that texel sample is going to go up and point at the actual real sample that I need to do. It's going to somehow get me there. But I have to do this, share this data across the whole page. So what I'm actually going to do is in that texel, what I'm actually going to store is the coordinates of the corner of the page. And then if I go back to the virtual texture coordinate and take a look at where that sample is relative to the corner of the page, I can use that same offset from the corner in the physical texture, and that gets me to exactly the right sample. So that will let me sample, pick an arbitrary spot in the virtual texture and find the right spot in the physical texture, but there's still a little subtlety that I need to handle here. The virtual texture on the left is not very useful. What was this? Oh, I just wanted to point out, hey, that's all the samples I need to fill in, and I'm not going to talk about the gray area yet. I'll come back to it. Oh, right, and actually I have illustrations for this. So I'm going to fill out all of this texture with each of these texels is going to get a pointer to the corner. I only bother doing the top row. So in some sense, I'm going to store the actual coordinates into these texels. So I've just populated them with numbers because the coordinates would be too small. Okay, now, so the limitation right now is that I just have this texture, and sampling from it is actually not very good because it really needs bitmaps before I can sample from it usefully, productively. So these are virtual bitmaps. They don't actually ever exist, just like the virtual texture. What we're going to do is we're going to divide those up into pages. We're going to use the exact same page size as the original pages. We're not going to have the same number of pages and have them have fewer texels in them the way a bitmap tradition works. Each page is going to be the same exact texel count as the pages on the previous level. Somehow I'm going to figure out which pages I actually need to have in the texture memory because I might sample from them or I'm going to sample from them. And those pages I just am going to download into this physical texture. Hey, let me zoom it in so make sure you can see what's going on here. I'm going to just download those pages, those new pages from the MIP levels into the same physical texture at the same MIP level. They're all packed in, all the MIP levels in this one texture. So you can see the glowing eye. There are 4 copies of that glowing eye at the 4 different scales. Once that data is all in that physical texture, I now need to be able to get at it. So I'm going to do the same thing. I need page tables that correspond to these MIP levels, and they're, if you look, you can see the number of pages decreases in a sort of MIP-map fashion. So I can just MIP-map my page table. I'm going to have 4x4, 2x2, and then each of those things I'm going to populate with pointers to the corners of those physical textures. So now, if I want to sample from some virtual texture coordinate that happens to be another MIP level, I'm just going to do the exact same operation. When I see that sample, I'm going to go find the corresponding MIP level and the corresponding texture coordinate that's going to give me a pointer to the corner of that physical page. And I find the offsets in the virtual space and offset that the same amount in the physical texture. So when I'm implementing this system, what I'm going to try to do is implement exact texturing in the sense that if I had that physical texture actually existing just as a regular old texture, not physical texture, if I had the virtual texture, if instead it was actually just a real traditional straight up texture ready to go, and I sampled from it, I'm going to get the exact same results with this virtual texturing system. There's just not going to be any loss. That's only true within round-off error. I don't mind if there's some round-off error, so there's tiny fractional differences. And this is only as long as I have enough memory and download bandwidth and other limitations to get the data into the system. But so as long as I can get all the data that I need into the page tables and the physical textures, it's going to try to be exact. So for the rest of the talk, I'm going to talk about how the pixel shader works in a very simplified fact. I'm going to leave out some details, and then I'll talk about the texture management, and again, leave out a lot of the detail. Then I'll go back through the pixel shader with a lot more detail, and not hide anything. And then I'll wrap up with some more talk about the texture management and some extra issues. All right. Well, I've walked through the basic operation of what has to happen at runtime with the pixel shader with all those illustrations, but now we need to actually kind of translate that into code. So here's one thing that you can think about as an example of how this might work. This is how virtual memory works. There's this virtual address, and the hardware needs to somehow do this virtual memory very, very fast. So it uses this bit extraction process where it can just look at the virtual address bitwise and pull out the top bits, and the top bits become the page number, and the bottom bits become the offset within that page. So it translates the page number and uses the bottom of it as an offset. So that's what it does mathematically. It does these bit operations. With texture coordinates, we have floating point. So I'm not going to do bit operations. But if I look at this floating point number as a binary float, so I have a decimal place and a string of digits because I'm assuming the texture coordinates are 0 to 1, then you can still imagine doing the same operation. You use the top bits to index your page, and then the bits below that can index which texel within that page. And then the bits below that actually are for bilinear filtering or subtexel precision. And I'll just, to try to make it a little clearer, I'm going to only pull out the texel indexes. Now, how do I pull those bits out in a pixel shader? It's very straightforward. If I multiply by a power of 2, I can slide that decimal point down until it's below, between the page and the within page parts. And then if I use floor and fract, I can extract the part above the decimal place and the part below the decimal place. Now, to access a page table, what I was saying here is that, hey, I'm going to use those top bits, and the way to get at those top bits is to multiply and take floor. But it's actually a lot more straightforward for accessing the page in our case because of the way texture mapping works. If I have a sample in this virtual texture coordinate, it's very obvious that to sample the page table, all I need to do is sample the exact same virtual texture coordinate. If I use nearest neighbor sampling here, so I always pull out exactly the data that's in that texel, that's just going to give me exactly what I want. So the first step of the shader, here I'm using GLSL. They're pretty much identical to what you get in HLSL. And I'm leaving out the types of the variables, but I'm going to add an underscore TC if the variable is a two-dimensional variable and it's used for textures. So the accessing the page table is very straightforward. I'm just going to access it with the virtual texture coordinates, and that's going to give me this page table entry. I'm going to hand wave the precision issues here and just say that what it gives back to me is exactly the physical texture coordinates of the corner of that page. At that point, all I need to do is find the offset within that page that I need to add to it. But there's a little subtlety here. The amount that I need to offset by is going to depend on the MIP level of the page table here. And let me explain what I mean by that. If I'm sampling from this particular virtual texture coordinate on the left, I have some particular offset, and then I'll use the same offset in the physical texture here. If I go to the exact same virtual texture coordinate at a different MIP level, so here I'm sampling the exact same spot on the guy, you can see that the offset from the corner of the page is different. And let me draw that larger. Here's a texture, a very simple texture, and here's one of the bitmaps of it. So there's my virtual texture, and here I've divided it up into pages. Both of these textures cover the same texture space. That's how MIP mapping works. You use fewer texels to cover the same space. So another way to draw this diagram, I'm just going to scale up the one on the right. So to make it clear that they're covering the exact same S&T coordinate space, and the one on the right is just using larger texels to do it. So in this case, it should hopefully be very clear now. If I try to sample from the exact same space in both coordinates, you can see that they fall in very different locations on the page that they're in relative to the corner of that page. There's two ways you can approach making sure you get this right. How to make sure you get that offset that's MIP level dependent. One way that's kind of straightforward if you want to try to implement it from scratch and make sure you get it right is to take these S&T coordinates that are fractional from 0 to 1 and rescale them so they're actually in texels, measuring off into, each texel is one integer 1 step. and because of because these have different number of texels, when you do that rescaling, the range that these cover will actually be different at that point. And once you're measuring in texels, you can modify the page size. The page size is constant, and that will actually pop out exactly the right answer you want in this scaled space. I don't want to scale the space and then unscale the space, so I'm going to work directly with this premise that I was talking about before. But you might have an easier time conceptualizing and tracking things when you're implementing it if you try it the other way. So how do I do it this way if I'm trying to think about this float and extracting things? Let's talk about the simplest case. If I have, as I keep mapping up the page table, eventually I reach a point where I have a one by one page table level. There's only one page, and it covers the entire virtual texture coordinate space. So here's that case. I have this one page, and it covers the entire virtual texture coordinate space. Well, what is my offset from the corner? Well, it's the virtual texture coordinate, because that's just, by definition, that's how this is set up. It's covering the whole space. And what that means is that in this case, if you imagine that I need 7 bits because I have 128 by 128 page, just hypothetically. On this level, I just need to use the very first 7 bits below the decimal place, because I'm just actually using directly unchanged the virtual texture coordinate as my page offset. If I go to 2 by 2 bitmap levels, then on each coordinate, I need to grab 1 bit so that I can select from those 2 by 2 pages. And that means that the within page coordinates are going to be the bits immediately below that, so I'm going to need to get shifted over by 1 bit. If I continue going down the mid levels, I keep adding bits in the same way. So by the time I'm down to the 16 by 16, I need 4 bits on each coordinate to index into 16 by 16. So I'll need to shift down by 4. So the shifting amount follows this simple pattern. It just keeps incrementing. And if I name my MIP level so that the 1 by 1 MIP level is MIP level 0, if I use that by convention, and then the 2 by 2 is MIP level 1, then I can just say that the shift amount that I need to use is the MIP level. So if we go back to the shader now, I'm going to compute my within page texture coordinate, and then what I'm going to do is I'm going to take the MIP level of this page, which I'm not explaining yet how I get it, and I'm going to raise 2 to that power and multiply by it. That shifts my decimal place down, and I'm going to take fract. And that will give me just the fractional part, which is going to just be the bits below the shifted decimal point. Now, at this point, I'm generating an offset within the page that because it's fract, I've scaled it so that it goes from 0 to 1. That's not actually the scale that I need. I need to actually address my physical texture here at the bottom. I need to use an offset that is the thing shown in white. I need this thing that's totally relative to the texture size, the number of pages in it. So I need to do the scale factor to convert between those two. So here I'm showing that scale factor. I'm rescaling from these page coordinates to the physical coordinates. And the exact value of that is just the number of pages in the physical texture. You need the reciprocal of the number of pages in the physical texture to do that rescaling. At that point, I've got that offset from the corner. I've got the corner. I just add them together. That gives me the physical texture coordinate. And now I can start sampling from that texture and get some actual useful data out of it. So that's the shader. Let's talk about this basic issue here of how do I possibly get these textures, have the right data, do that in any sane fashion. So the answer to the question of what textures do we need, there's some different possible approaches. The approach that I'm taking and the approach that I understand in software, at least they were taking a year or two ago, is I'm going to render the scene in extra time and find out what textures the scene needs. So what I'm going to do is I'm just going to go ahead and render a first pass, the entire scene. I'm going to use a special fragment shader that is determining where in the virtual texture we would want to sample, and just writing out some identifiers for which pages those would be and what MIP levels it needs them at. Once I've written them out, I can just read them back in the CPU, and that will give me a list of a collection of page identifiers and MIP levels, and I just need to find all the unique ones. And once I've done that, I got exactly this data that I wanted. I got a set of pages and the MIP levels, corresponding MIP levels that I need for those pages. So that's it. That's exactly the data I needed. Now, what do I do with that? Oh, right, okay. Uh, so I have the only thing is so that data like has this fairly direct translation that I've already talked about, but I've been skimming over this problem of what do I do with all this empty space. Um, well, why do I care about the empty space? Well, the shader is as it's written uh, is assuming there's going to be a physical page data available, assumes that there's a valid page table entry and goes with it. So in that blank space, what happens if I don't put valid data there? In a virtual memory management system, this is a page fault. This is you trying to access unmatched memory, the memory that's been swapped out to disk, perhaps. In a virtual memory system, the virtual memory system has to halt your process and swap that data in. There's nothing it can do to get around that. You might be accessing a pointer and it needs to dereference that pointer, and there's really no option. Your program has to produce exactly correct results. Virtual memory has to be totally transparent. You can't tell that it exists other than the performance overhead. In graphics, we can tolerate wrong output as long as we're not trying to do generalized computation with the GPU. So we can hack around this particular case. We're in a pixel shader. We can't stop. We need to just produce something. It's, whoa, let's do it. And the solution here that we've often used in other situations when we don't have the texture data we need yet, because say we're waiting for it to stream from disk, is we use bitmap level. So we're going to do the same thing here, but we can do this on page granularity. I'm not going to do it in the pixel shader. I'm not going to have the pixel shader look and say, oh, that data is not there. Let me look up. Let me look up. Although somebody proposed that, somebody came up to me after the GDC lecture I proposed that maybe that was actually a good idea. And I need to think about it more. Reflexively, it sounds dangerous, but the overhead might be rare and might save some other costs. I didn't get his name. Let's see. So mipmaps. So I'm going to substitute mipmaps, and I'm going to substitute them on a page granularity. So here's just what I've got in the hardware. I've got my physical texture, and I've got my page table and the mipmaps from my page table. And I'm going to do that same rescaling. I want to make it more visually clear that the pages, the mipmap pages, still cover the exact same total texture coordinate space. So here's the same data rescaled. I rescaled it in Photoshop. So the fonts are not pretty. So we can keep track of what's going on. I'm going to color code it, which I also did in Photoshop. So I'm going to make this right, as I numbered them before, the 0th bitmap is on the right. So there's 0, 1, 2, and 3 across, and that's too confusing. So I'm going to color code them and circle out the colors. So there's the most detailed level on the left. There's a blue level, a magenta level, and an orange level. And I'm also color coding it because of what I'm about to do. If you look at 27, the blue top left page, you can see that geometrically that's covering the exact same coordinates on the far left as this. It falls right there. So what I'm actually going to do is I'm going to take those page table entries, right? These are just texels. This is a page table, so each of these is a texel. I'm going to take that texel and I'm going to write the exact same texel down here on the left in those blue squares. And I'll talk about later why I can pull this off. So I'm going to go ahead and propagate all of those blue ones down into this level. And I've still got a lot of dead space that I need to fill, so I'm going to go up and start copying down the magenta ones, and then once those are done, I'll copy down the orange ones. Now, at this point, that page table is totally full of totally valid data, so anywhere resampling it is going to be referring to something that's actually present on the hardware and produce some result. It may be a bitmapped result, but it's a result. I still need to do the same thing for these other page tables because we can sample from them. So I'm going to fill in each of these levels in turn. So when I fill this level in, I can only fill it in from levels above it, the less detailed levels, the levels where the pages cover more data, because I need to make sure the page covers, the page that I bring in covers the entire region. If I try to bring in from below that the more detailed regions, those pages don't cover the same region. The reason I need to do that is because for the bitmap substitution to work, we're going to need two things to be true. Whatever page we end up choosing needs to actually contain whichever virtual texture coordinate we're at. As long as that page covers it, it doesn't matter what bitmap level it comes from, we can make this work. The reason we can make it work is as long as we know what bitmap level the page entry that we just loaded refers to, what bitmap level that physical page represents, then we can do the correct scaling to compute the offset within that page. So as long as we know the bitmap level that we used to scale the page, that we need to scale the page that way, we can make any page, any MIPS page that we happen to load work. To make that work, in the page table entry, this texel is going to actually contain the coordinates of the physical page, and it's going to contain the bitmap level. And that way we have all the data available in the page table entry, so when we copy the page table entry around, we get exactly what we need. I'll talk about this in more detail when we come back around, but just since you might be wondering, this how much data do I use? So when I demoed this originally, I was running on a laptop, and that's what these slides are referring to. Oh, actually, this is all still true. So I am running a K/1068, and I have allocated 4 million physical textile samples, but I don't actually use them all. So this is actually running on a GeForce 7300, and there's some weird performance problem that I haven't, some weird glitch has started, but I'm not sure what it is. My frame rate is spiking in some very random way, and profiling is not showing anything, so I'm not sure if I've got a driver bug or what, but I'm probably doing something stupid in the code, but it didn't show up on any of the other platforms, and it wasn't doing this for most of the development of this app. So I don't know if that turns out to be visible here, but and I was wrong before when I said this was 64K by 64K. This texture down here is actually 128K by 128K, I think, and the 64K by 64K one was on the laptop. You can see this very bad bump map, these circles. That's kind of hacked in, but that is also a virtual texture. It just happens to be repeating because I didn't bother making a procedural generator or do anything interesting with it. So as I move through the world, I can take a look at how many textures I'm actually using, and it looks like generally I'm probably only using about 2 million of those 4 million texels. But I have 4 million available for the worst cases when I need more than 2 million, and the extras turn into cache. So when I come back and look at something that's suitable. Plus, I'm going to need page table texels. In general, the amount of data that I need is proportional to my resolution. As my resolution increases, I'm going to need more texel data because everything's running at sort of the ideal resolution, assuming you have unique texture data and data all the way down so that you always have detail wherever you go. If you MIP bias, you can affect that as you use your MIP bias to force things to look softer. You're going to need less texture memory. Although there's always going to be a worst case. The worst case for K/1068 is probably something like, well, I don't know, 4 million texels, maybe a little more. So I want to go back to the pixel shader, a lot more detail, and make sure I cover all the little significant issues. The main issues that I sort of skimmed over here were some minor bias issue, a significant precision issue, and the lion's share of the time here is about texture filtering. So I was just sort of hand waving and assuming nearest neighbor sampling on the physical texture. So the first is this bias issue. I've been saying that when we sample from this virtual texture, we want to sample from it at some MIP level, and we're going to use the corresponding MIP level in the page table. How to get the corresponding MIP level? There's a bias operation that needs to happen here because the page table, these are texels, and so it's only going to automatically MIP map when those texels become 1 by 1. I'll switch, or smaller 1 by 1 pixels is when it'll switch to the next MIP level. But I want to switch when the virtual texture would have switched, which means when the virtual texels would have become 1 by 1 pixel. So there's just a bias that I need to have there. It's log2 of the page size. It's very straightforward, just an easy little detail to forget about. So now I said I'm going to actually go ahead and pack some extra data into my page table. So I want to be explicit about this. I have this page entry. I'm going to store the red and the green channel. I'm going to store the coordinate, the page, the physical coordinate, and the blue channel is going to store my mid level. So here I've replaced the exponent 2 of the mid level with the exponent 2 of page.b, the blue channel. This code doesn't actually work as it is because that's not the, I don't want to exponent number. Depending on what texture format I use. And I want to actually now go ahead and use an explicit texture format, a very simple one. I'm going to use RGB 888 and just store what show up in the pixel shader as these floating point numbers from 0 to 1. And when I'm feeding them in the software, I'm writing out unsigned bytes. And what I really want to do is get back those unsigned bytes. And this is how I do that. This is not necessarily the most efficient approach. Depending on what platform you are, you may have a more straightforward approach that you can do to do it safely. I don't know. But I just multiply by 255 and round, and on all the hardware I've tried, that produces exactly the integer results I really had. Not necessarily very efficient, though. If I do this, now I've got my page in my page.b is now the mid-level actually as an integer. It's exactly what I want, and I can do the rest of this. But I actually do this not just for the blue channel, but also for the red and the green channels. And this is how I avoid any precision issues for expressing those coordinates. So now I'm expressing those physical page coordinates as integers. As I'm saying, I'm just using these coordinates that are integral and saying which page through the thing is it. Because those are integers, and the within texture coordinate that I compute with the fraction is already 0 to 1, I can just add those directly. Those are in the same space, although it's not the final texture mapping space. And then I do the rescale after adding them, where I used to be doing it before. And that brings it into the right thing. You can sit down and draw it out, and it's fairly obvious. I want to translate this to assembly just so you can see how much work goes on here. I'm not going to talk about this in detail, just want to point this out. This is GL fragment program, should be pretty similar in other things. So I've got 9 instructions so far, and that's including the final texture sample. If you're just sticking like on the front of the shader, it's 8 extra instructions, and one of them is a texture instruction. And then the dependencies, you're going to be waiting for that calculation before you can make the final, your actual texture access thing. Now, if I turn on bilinear filtering in my physical texture, I have a problem. That's not going to produce that correct result. Right along the edges of the pages, when I sample those, the bilinear filtering is going to start sampling adjacent texels. Some of those texels will come from the next page over. That next page over is totally randomly decorrelated from the actual page I'm in. So I'm just going to start blurring in this, filtering in this data that's totally irrelevant, not the right data, and you'll get lots of sparks artifacts along the edges. Now I could try to address that by doing the bilinear myself and making multiple virtual samples, but that would be massively inefficient. So instead I want to make sure I use the texture filtering hardware to do my filtering. Well, the solution to that is very straightforward. I need to pad those pages with extra data. That is the data that comes from the virtual texture that is immediately adjacent to those pages. That texture data might exist somewhere in the physical memory already in some other page. That's fine. I'm just going to be making having extra data here. So, hey, here's my page. Here's the padding that I need to add to make that work. I actually pad around both sides. So this adds 1 texel in each axis, and I add 2 texels in each axis. I don't think that that's necessary, but it was probably saving me from fixing some precision issues. And hey, you could ship with padding on both sides. Not that bad. Now to make this work, my effective physical page is slightly larger, and I need to deal with that because most of the math I presented is working directly on physical pages. So particularly the within page texture coordinate, naively right now, what I used to have was the thing on the left, and the thing on the right is the natural implementation at this point. My texture coordinates are going to actually still cover those padding pages, and if I just turned on padded and turned on the bilinear filtering, I would be rendering those padding texels as if they were regular texels, and I would still sample off the edge of this page. So what I need to do is contract those texture coordinates in the map to actually bring them back so that the natural naive texture coordinates don't touch the padding, but it's the extra bilinear samples I'm ignoring the exact details of the page centering just to try to make that so I can state that unambiguously, but it's a little similar. You might notice if you're padding like this, it's no longer power 2. If I started with a power 2, the thing I have now is no longer power 2. Or I can kind of contract. I can start using a smaller physical page size, naive, a logical page size that's smaller and pad it out to a physical page size that's power 2. And it doesn't really matter. You can actually use a page that's 100 by 100 and that pads out to 101 by 101 because we're not doing bit operations to extract things. We're doing floating point operations. However, on the other hand, those floating point operations have some limited precision, and it's much nicer when the math under the hood is only multiplying and dividing by powers of 2 because you know you're not losing any precision. So I've opted for making sure that the physical pages remain power of 2 in size, and the generally it's the software that mostly has to deal with the fact that the physical, the logical page is no longer power 2, but also that has pressure on the art. It means that the full size of the virtual texture in texels is no longer a power 2 either. And if you want to use these textures and have them wrap, you might find that now your dimensions that you need a texture to be to wrap are no longer a power 2, but are contracted in the same way. So to do this, to actually implement this, here I'll just show it in the assembly version. I just have to add this one instruction. I need to do a multiply add to do this contraction of my S and T coordinates. So I'm just multiplied by this ratio, the ratio of the logical and the physical size. And if I pad on the left, I also need to add an offset. And maybe you need to add an offset of like half of texel or something like that if to deal with the centering correctly that I hacked by padding. You can do a simpler shader than this. This is something John Carmack mentioned to me in email. With if you're willing to use a floating point page table texture, so your texels are floats, so your page entries have fairly arbitrary precision. You can do something that's a lot more precise and kind of fold all these, everything that's page constant, so that's the data you get out of the page table and all the data that's constant across the entire virtual texture. You can fold all that computation together, and there's it's possible to actually get rid of the fract function using that, and everything else is pretty much just multiplies and adds. And so it turns out if you collapse all that math down, you can end up with just one multiply add. So you sample your page table entry, and that page table entry now has exactly the numbers that you happen to need in the pixel shader to do this multiply add. So you multiply add on your virtual texture coordinates to produce the physical texture coordinates, and you can immediately address your physical texture other than the actual dependency delay. So that's just, I've never tried implementing that. I don't know how interesting that is because it does increase your page table size. And depending on I just don't. I have no clue. Never tried to do it. All right, trilinear filtering. We want to turn on trilinear filtering, so that's how we turn on bilinear filtering. So we want to turn on trilinear filtering, and again, it's the same thing. We want to use hardware filtering. I don't want to just sample myself from two separate MIP levels to make two separate virtual MIP level samples and wait between them myself. I want to use the hardware filtering. This is what's currently in the hardware that right now. I've got a page table that's MIP mapped. I've got a physical texture that's not MIP mapped. I've just got one level of the physical texture. I've packed together all the different MIP levels into that one texture. But I want a triler, and I want to triler the physical data, so it's very straightforward. I add one MIP level to the physical texture, just one, and it's just got MIP maps of all the pages. This is very straightforward. Now, what happens is the issues that I have to be careful about are I have to put in padding into the MIP levels. That MIP level is also doing a bilinear sampling, so it has the same issue of like page boundaries. So I need to make sure those page boundaries are padded. If the MIP level has padding, has like a one texel padding, then the course's mid level needs to match. So it needs 2 texels padding. So along each edge, I need to put 2 texels of padding. And so in my demo, I actually pad all edges on both sides with 2 texels. So the actual dimensions I'm using in this demo, it's probably too small. I'm using a 64 by 64 page. So it's actually a 60 by 60 page with 2 texels of padding on all sides. The other thing we have to be careful about is that our MIP transitions are still going to work using the page table MIP mapping, and we need to make sure that we get exactly the same results continuously across that. So if I'm lerping between, so if I'm, the trilinear operation is lerping between these 2 levels, these 2 samples in the physical texture, and as I lerp, as the lerp weight goes to 100% and reaches so it's 100% of the bottom sample of the course MIP map level. When I reach that 100% level, I need to transition and start going to even smaller things. To do that transition, the page table, I'm going to switch to accessing this totally different, totally unrelated page that lives somewhere else in memory, and it's got its own bitmap. And I'm going to start trilarping between those. And when I do that transition, there's this sort of discontinuity because I'm switching the pages. So all I need to do is I need to make sure that these 2 pieces of data, one is the MIP level of one, the MIP entry, the MIP data, the once MIPed data for one MIP level matches the raw data for the other MIP level. I need to make sure those match. As long as those have exactly the same texels in them, then that transition will be seamless. So basically, I'm going to use the same shader, and I need to put in more padding. That seems like that basically works, but there's a problem. When we get down to this sample, the final sample operation in our shader, and we hand in these computed physical texture coordinates, those fractional texture coordinates are computed. This texture operation, now that we're doing trilinear, needs to compute a fractional MIP level to weight between the 2 samples. Before we added this trilerp, I only ever had one MIP level of this physical texture, so it didn't do any MIP mapping at all. It never needed to compute MIP levels. But now, at this stage, it needs to compute the MIP levels. We only need it for the fractional weight between these 2. To compute this MIP level, the hardware, the math requires computing the partial derivatives of the texture coordinates. Now, as I've written this, how do we get those partial derivatives? It's up to the hardware and the driver to do something here. And on this hardware that I'm running currently, the GeForce 7300, how it does that is with finite differences. It takes 2 samples at 2 pixels that are adjacent to each other and looks at what those do. So here's the virtual texture, and if you look at those 2 samples and you look at the delta between them, how far you step to get from one to the other, that difference between them is an approximation to the partial derivative. And in the case of raw texture coordinates, something else is actually done. And it's done analytically and produces the right results, I think, or at least it used to be. But when we go through our mapping using a sparse virtual texture, we end up with 2 samples that just come from arbitrary places across when that step occurs across a page boundary. It now is sampling from these 2 random places in the texture, and the difference between those is this huge step that's stepping all the way across the texture. If you use that as an approximation for the partial derivative, the texture filter looks at it and says, wow, that's a gigantic step. The way I handle gigantic steps is by blurring them extremely, so I want the coarsest MIP level possible. I only have 2 MIP levels, so it forces it to that second one. Now let me demonstrate this. Here's the terrain. I'm going to turn on this MIP coloring. So this is showing the MIP selection in the page table. I get a different color for each when I switch MIP levels in the page table. And I'm going to turn on something to show the trilinear filtering as well. So what this does is I've turned the coarse MIP level of the physical texture, I've turned that white. So what happens is as I trilarp between the detailed level and the coarse level, it goes from the actual data to white. And so then there's a MIP transition and I start over again. So you can keep seeing how it goes from colored to white and immediately goes to the next color and that goes to white. It goes, etc. But you also can see here all these lines. Those lines are the page boundaries. But the only reason I'm not drawing those lines are MIP computations that are turning out wrong. The MIP computations are jumping out to the white level. They're going to the coarsest level possible. And that's happening because of the finite differencing that I was just talking about. Yes, I meant to show this demo first, and so you might now want to rewind to the stuff that listen to the stuff I just talked about. So the solution to this problem is to go ahead and compute the correct gradients and use those in the texture sample instead of having the hardware try to figure it out. Because the hardware has no idea what we're doing, doesn't know what the right behavior is, because we're relying on how we pack that data. There's no way for it to know that we pack that data in a particular way, but there's this answer. And the way you can compute the correct gradients is you can take the partials of the virtual texture coordinates. Those are always coherent, as I was showing in this illustration on the left. Those are always well behaved. So if we take those partials, we'll need to do some rescaling to scale them back to the coordinates we need in the physical textures. You have to make sure that you take the partials and then scale them. Don't scale the virtual texture coordinates before taking the partials, because the scale factor actually has a MIP dependency on it, and when the MIP level changes across the page boundary, you would get the same artifact. So in GLSL, with an extension that adds gradient support, that adds a whole bunch of work that we have to do here. It's fairly obvious, so I'm not going to talk about it. GeForce 7300 that I'm running on here does do GLSL, but it does not support the this feature set. So I have a hack that I use on hardware that doesn't support the feature set. It's kind of ugly. I'm not sure it's really shippable, but it happens to work in this demo for most things. So the case is, if you have hardware that doesn't have gradients, there's no way to just directly specify the MIP level either, and doesn't let you specify the gradient for the texture sample, or doesn't let you specify the MIP level directly. If it does let you specify the MIP level directly, but you can't get gradients, there's probably a hack you can do, sampling a texture with MIP mapping. So you could probably compute the MIP level without gradients, a decent approximation to. So assuming you don't have any of that stuff, you don't have any way to control the texture sample. If you don't have any way to control the texture sample, here's the hack that I do. I don't have any nice illustration of this, sorry. So I can't prevent the texture hardware from drawing the wrong map level sometimes along the page edge, and that causes synapse flickering. Not as bad as what I was showing when I turned on this debug thing, but there is some flickering and popping that you can see, and sometimes the map texels at a given spot are surprisingly different in color. So you can see pretty significant artifacts. So what I do, since I can't prevent it from sometimes drawing the wrong level, is I make it always draw the wrong level. I don't do that in the pixel shader, but rather I replace the data in the detailed texture with the data it would draw if it drew incorrectly. So along the page edges, just only the texels right along the page edges, I go back to the MIP and I upsample those back, upsample the edge data from the MIP maps back into this thing. That means there's this weird softening everywhere. I didn't do it on the slides because it made the slides look really bad. So yeah, I don't know if that's that useful. This also violates some of the exact match stuff, so you give up. You can see a little more popping when you switch map levels. And in fact, to avoid that, I don't exactly do what I just said. I sort of do a weighted average between the upsampled data and the original data. So there's a little bit of artifacting along page boundaries that's very hard to ever see, and it slightly reduces the MIP transition problem. Again, this is only necessary to do trilinear on hardware that can't do it. You could just not do trilinear on hardware that doesn't have this feature set. So it's got this exact match problem that if I do this propagation, I'm sort of changing the data that I have in my physical texture, and there needs to be this correspondence between levels, and that propagates really badly. It's really ugly, so I don't do that, and that's why I was saying I get that popping. It's because I don't bother having that exam match. You can do anisotropy to continue the trend, bilinear to trilinear anisotropic filtering. To do this, you'll need even more padding around the edges, as much padding as the number of taps in the filter, or half the taps. I'm not positive. I didn't try implementing this. You absolutely have to have gradients because that's exactly what the anisotropy needs. So you need the correct partial derivatives. And you're going to need more texture data. You're going to need more texture data because you have more padding. You're going to need more texture data because that's the anisotropic filter uses more caps on a more detailed version of the texture. That's how that works. All right, that's it for the shader. That totally covers the shader. Now I want to talk about how to make this texture management actually feasible. So I'm going to do the readback that I was talking about. I meant to demo that. Well, let's go ahead and show that now. So here's that. Here's what I'm actually writing out and then reading back. The red is the bitmap level. The green and the blue channels are 8 bits of the page identifiers. There's some more bits though. So there's not much to see. You can see the bitmapping going on here pretty clearly. The only thing is that this doesn't necessarily perform very well, especially on the laptop I was demoing it on, so I downsample it. I use this lower resolution version of this. To make it run on the laptop reasonably, wrong button. Here we go. I do this incredibly tiny thing. I've dropped it by a factor of 8 in each dimension. I can get away with that because my pages are 64 pixels by 64 pixels, and they're always approximately 1-to-1 with pixels. So even though so if each page is always going to come out on screen is, I don't know, at least 60 by 30, well, for shortening. If I drop it by a factor of 8, I'm still always going to hit a sample from the page. But I would start missing very thin objects if I had objects that were only 6 pixels wide. I might miss them entirely. This only works because I don't have those in this demo, I think. So I don't think you can get away with that much of a reduction of this. But you might be able to cut this down by 2 in each dimension without a noticeable loss. You might miss samples from 1 pixel wide objects, but if a 1 pixel wide object, you probably want to reduce it to a fairly low mid level anyway. Like it might be edge on. If I manage to make this very extremely edge on to the point where it doesn't show up anymore in this thing. If I made it so I'm not really producing all the samples here, it's going to be at an incredibly coarse mid level anyway, because it has to be because it's edge on. Okay. If I'm using this algorithm, I have some problems. I can't handle transparency. I'm writing out to this frame buffer 1 result at every pixel. So the only thing I can put in there in that 1 result is the opaque pixels. So I'm only going to be able to get back data that I need for opaque pixels. So I'm going to need to do something else for transparency. I either don't put them through the the sparse virtual texture, or what I give away, or I or I could try to do some kind of analytic thing about what I need. One of the nice things about the readback, I could do an analytic thing for the regular data as well, for the opaque data. But one of the nice things about this readback is it actually gets us not just what's in front of the camera, not just what's near the camera, but it gets us occlusion as well. So if something's occluded, when we get to the readback, we don't see it at all, and we don't bother thinking we need the texture data for it. That's a really nice leveling advantage. It's something that tends to keep the amount of texture data that we need much more consistent than it would otherwise. So that's why analytic is probably not a good idea there, although maybe you could make it work. But for the transparency, with transparent stuff, we don't get occlusion anyway, so we're not really losing anything from, in that case, going analytically. There's a subtlety with anti-aliasing. If you look at this, if you think about it, the anti-aliasing is going to be generating an anti-aliased pixel is going to have used more than 1 sample to generate that pixel, and that means we're only writing out 1 sample there. But this is basically the same issue as what I was saying about downsampling that readback. It's probably not a problem. The places where it's going to occur, either the detail is going to be too small to ever notice, or it's got adjacent pixels where you want to pick up the needed page identifiers. And there's a worst case here. If you have rapid rotation like mouse look, you might need a ton of new texture data as you spin around. There are actually other worst cases without mouse look, like sidestepping while staring at a wall. There's not much you can do about this. You could try to download the data that you need in all directions at once, but you're going to need a lot more data in that case. And this is a big problem if you're doing procedural generation. Although there are cases where that might balance out. And it's going to use a ton more texture memory. So if you have texture memory issues, that would matter. You may not have as many issues with it since you get to use less data anyway. So I don't have any good answers for this. Hey, this is a tech demo. I'm not trying to ship a game. One nice thing though that we get is we do get this bitmap substitution thing that we can do, and we can apply this to a lot of cases. If we don't have enough texture memory for all the pages we need, we can substitute bitmaps using that bitmap pages. If we were procedurally generating, we can limit the amount of procedural generation we need to do per frame, or we are limited if we're running the procedural generator on a particular one core or something, and it's bounded. We can start substituting bitmaps if we can't generate them fast enough. Or if we're streaming from disk, obviously we substitute the bitmaps for data that's not there. This is going to result in pop-in. If I turn on the mid levels, visualize, I can make this really obvious, assuming this hardware isn't so fast that I run it. If I run up to a wall and stop moving, you can see the data draw in after the fact. Now, if I don't have the mip mapping debugging on and I do that, it's a lot less obvious, but there is some pop-in. You can see things get crisper or sharper after you stop. I didn't actually that time, but it does happen. And if you have any offset issues in your MIP levels, if your MIP levels like shift by half a pixel as you go up the MIP levels or something, try linear. I think there's some weird popping out here. I don't know what that is. Why those are moving. I don't think it's what I was just starting to talk about. Trilinear usually hides that kind of shifting. But if there's popping, you'll actually get a chance to see the shifts. I wonder what the heck that is. Am I drawing quads? And no, that doesn't make any sense. Huh. I know what that is. So that's just the one drawback to doing that. The bitmap substitution. The biggest drawback to that is you will see popping. But as long as you can meet your constraints, it won't be that bad. If you're always like if your procedural generation is like if you're fast enough but you have to be have latency, so you're a frame or two behind all the time, you probably would never actually see it popping. Here's the algorithm I use to manage all this crazy data. We start with this algorithm I was just talking about to determine what pages we need. Once I got that list, as a simplification, I say that I need all the bitmaps for all of the pages, for all of those pages. So every bitmap level above it, every course or bitmap. That's not usually too much extra data, and that allows me to use an algorithm beyond here that is basically optimal. So all I need to do at this point is if I've got more pages than will fit in the texture memory at this stage, I start dropping the pages. I drop the highest resolution pages, that is the pages with the smallest texel, the texel size in world space is the smallest, or really in screen space is what I want, but however you want to prioritize that. But now I'm going to start downloading the data, but before I do that, if I got any data in the texture, in the physical texture that I need for this frame, I'm going to lock it to prevent it from being discarded during the rest of this operation, because it would be really moronic to discard something and have to regenerate it. So once those are locked, I'm going to start downloading pages, and I'm going to decide where each page goes. I'm going to do a least recently used algorithm to remove pages and the pages that get replaced. And the reason I'm doing that is so that if I have extra data, that data serves as a cache. Now I mentioned that we might have a limited download bandwidth or procedural generation, and if that is limited, the minor alteration to that algorithm is when I start generating and downloading these pages, I'm going to do them in order, starting from their lowest resolution to the highest resolution, or again, in really measuring the textile size in world space or screen space. And if I do that, as I download these pages, I just stop when I hit my threshold of how many pages I'm allowed to work with. Doing that by going in the right order, because I required all the bitmaps, that guarantees that I get the substitutions that I want in the page table that are sort of optimal for the speed I'm moving at. So if I move through the world at a high speed, I may never download those highest resolution textures because I'll get a request for the high resolution texture. It'll be deprioritized. If I stop moving, if I just moved here, then the next frame I'll try for that page again, and this time it'll get downloaded. But if I'm still moving at high speed, I might never download that page, and I'll actually then go past the scenery that needed that page and stop requiring the page entirely. So at high speed, I'll start just entirely never bothering to download these highest resolution textures, even though they would all fit in memory, just because I have this procedural generation constraint. Now, as I'm swapping and as I'm replacing pages in my physical texture, I need to update this page table. And what does that mean? Well, so if I swap out a page, if I remove a page, I need to remove it from the page table entry, the matching page table entry, and I need to put something else in there that will work. So what I'm going to do is, let's say this 25, and so the second from the right, there's this 25 at the upper left. Say I'm unmapping that page. I need to replace that texel with something else. I'm going to replace it with 24 because I have to propagate from above it. But also, I'm going to go through check all the descendants of that 25. So all the textures to the left that correspond geometrically, and also update those. So either dynamically, I'm going to go search them, or I'm going to have kept a list to know where they are. And I'm going to go through and replace all the 25s all the way to the left with the same whatever item I did for the first time. So they're just all going to get replaced on 24s. Same thing in reverse. When I map a new page in, I have to replace that page, and I have to go through its descendants and see if they need updating as well. So if right below the 25, where I have 24 right now, if I swapped in a new page there, say I called it 32, I would now go to the left. There are some 24s in the same area, and all those 24s would also get replaced by the 32. This is all pretty straightforward there. There's a hidden issue here, which is when you have more than 4 mitlab levels, which you will, when you get to 8 mitlab levels, these coarsest pages start having hundreds, 128 by 128 pages on the left edge that need updating. This is just some data that's far in the distance. You're only seeing this you just decide to swap in this page. It's this very coarse mid level, so it's very far off. It would be foolish to have to go update 128 by 128 pages when this is happening. It doesn't happen probably doesn't happen as much. I shouldn't say that. So what I do is I don't actually propagate that data all down to all descendants. I stop after, I think, 3 map levels to keep, so that the worst case is 8 by 8 that need updating. Just because the cases that we're trying to cover here, the degree of sloppiness we expect, it shouldn't ever be more than that. But that's a hack that I do. All right, and so doing all these updating all these pages, I'm going to be sparsely touching this page table a lot. So you need some kind of system that lets you update that efficiently. So some other issues to think about here. My page size. I can use some arbitrary page sizes in this demo. I happen to be using 64, but I suspect something like 120 or 256 are a better idea. But what are the factors here that matter? So I just noticed that I'm filming this on my digital camera, and it's going to fill up very soon. I seem to only have 4 minutes left, so I'm going to have to skip some things here. So the page table, the page size, there are some trade-offs here. I think you want larger, but although there are some advantages to smaller. But probably the most important thing is if you use a large page, like 256 by 256, you'll cut down how many page table entries you need. And that's probably going to be the biggest factor. So DirectX TXT texture compression, you probably want to do this, your pixel shader performance to keep your bandwidth needs per fragment down. You have a problem if you just take the existing data that I'm talking about here and texture compress it, because I said I want these exact matches. I want to have exactly the pixels here so you don't get any artifacts along the page boundaries. If you just randomly DXT compress the data, you're not going to get exactly the same data in those places. That's going to cause artifacts. The safest thing that you can do here is you take the coarse MIP level and pad it by 1 block, maybe on all sides, maybe only on the one side. And that means you'll need 2 blocks on the finest MIP level. That guarantees you just got blocks. You got exactly the same blocks everywhere, so you'll get the exact same data. An alternative in software has this paper that we've talked about doing dynamic compression, and they talk about doing this. If you use a DXT5 texture, use the YCOCG color space, and put the alpha into the Y, by separating the data out that way, you can get very high quality compression fast. It's high enough quality that it looks pretty indistinguishable, and I suspect you wouldn't actually get any noticeable artifacts if you used that. And you could just do that without worrying about the alignment and having the pad by as much. Okay, that's it. Thanks for watching.